Alright, so the goal of this video is to discuss prime and maximal ideals. So we'll start out with a commutative ring R, and the ring will have identity, and we'll let I be an ideal of R. And what are the goals for the video today? The goals for the video are to answer the question, when does R mod I become an integral domain? Right? What conditions does I need to satisfy for R mod I to be an integral domain? And when does R mod I become a field? So what conditions does I need to satisfy in order for R mod I to be a field? So we'll start with a motivating example. We'll start with the integers, and we know that when I look at the integers, I can construct the ring Z mod PZ and get a field, right? So I'll let P be a prime, and I know that Z mod PZ is a field, and thus an integral domain, because every field is an integral domain. So the question we're going to ask is, well, what's so special about PZ? What kind of information can we extract about this ideal PZ? So these are all the multiples of P inside of Z. Well, let's think about this. I'll suppose that A and B are integers, and A times B is an element of PZ. Well, let's dissect this a little bit. So then, I know that P has to divide A times B, and so, since P is prime, I know that P divides A, or P divides B. So hence, I can say that A is an element of PZ, or B is an element of PZ. So this is going to be our first motivating example. We're going to say maybe this is the property of PZ that causes something nice to happen. Maybe we'll get an integral domain, or maybe we'll get a field. Okay, so we'll start with the following definition. I'll let R be a commutative ring with identity, and I'll say that an ideal I in R is called prime if, for all A and B in R, whenever A times B is an element of I, then A is an element of I, or B is an element of I. And the thing to notice here is we're just mimicking this condition from above, right? So AB is an I implies A is an I or B is an I is just mimicking the condition that AB is in PZ implies that A is in PZ or B is in PZ. So we're going to call such an ideal a prime ideal because it's naturally motivated by the example above. So now let's look at some examples of prime ideals. Okay, so our very first example is the example of above. So if P and Z is prime, then PZ is a prime ideal. Okay, so this is pretty straightforward. One thing I'll point out is if we use a composite number, so for example 12Z, this is not a prime ideal. And the question you might ask is, well, why is this not a prime ideal? Well, I know, for example, that 3 times 4 is an element of 12Z, right? 3 times 4 is an element of 12, but 3 is not an element of 12Z, and 4 is not an element of 12Z. Okay, so 12Z is not a prime ideal, and the same argument can be made for any composite number. So the multiples of any composite number are not going to give us a prime ideal. Okay, and here's another example. I'll assume P of x is a polynomial in f bracket x, where f is a field, and I'll assume P of x is irreducible. Then it turns out the ideal that P of x generates is a prime ideal. So let's prove this. Well, let's suppose A of x and B of x are polynomials in f bracket x, and A of x times B of x is in the ideal generated by P of x. Well, then what do we know? Then, just like with our prime integer example, we know that P of x divides A of x times B of x, and we showed that irreducible polynomials have the property that if P of x divides A of x times B of x, then P of x divides A of x, or P of x divides B of x. So we could say, and so P of x divides A of x, or P of x divides B of x. Hence, we have that either A of x is a multiple of P of x, so A of x is in the ideal generated by P, or B of x is a polynomial multiple of P of x, so B of x is in the ideal generated by P of x. Thus, the ideal generated by P of x is prime. Okay, so this is an example of a prime ideal. Okay, so here's an example of an ideal that's not a prime ideal. So I'll take I to be the ideal generated by x squared inside of Z bracket x. And the question you might ask is, why is this not prime? Well, one thing I know is that x squared, which is equal to x times x, is an element of I, right? X squared can just be written as x squared times the polynomial 1. So x squared is in this ideal, but x is not an element of I. right? And the reason is that if we think about this ideal I, the ideal generated by x squared, these are all the polynomials of the form x squared times h of x, where h of x is an element of z bracket x. And these polynomials all have degree 2 or higher. So all have degree greater than or equal to 2. So x cannot be in there because x has degree 1. Okay, and finally we'll do a similar example, but this example will be a prime ideal. So now I'm going to consider the ideal generated by x inside of z bracket x. And I claim that this ideal is prime. So this is going to take a little bit of work to show. So the first thing I'm going to notice about this ideal is that the ideal generated by x are all the polynomial multiples of x. And I might think about what these look like. If I take x times a polynomial that results has no constant term. So what I might notice is that this ideal is just a set of polynomials with constant term 0. Okay, so with that insight, we can begin our proof. So I'm going to suppose I have two polynomials, a of x and b of x, and I'm going to suppose that their product is an element of I. Okay, well, then, what do I know? I know that a of x times b of x, if I compute what this polynomial looks like, it's going to be a0, b0, plus the x term is going to be a1, b0, plus a0, b1, times x, plus so on and so forth, is an element of I. Well, what does that tell me? So I know that a0 times b0 is equal to 0, right? I'm an element of I if my constant term is 0. Okay, but if a0 times b0 is equal to 0, I know that the integers are an integral domain, so either a0 is equal to 0 or b0 is equal to 0. In other words, I have a of x is an element of I or b of x is an element of I. And so this is an example of a prime ideal. Okay, so we're finally ready to answer the question, why are prime ideals so important? Well, it turns out that prime ideals are precisely the ideals that make R mod I into an integral domain. So we have this nice theorem here that says, suppose R is a commutative ring with identity and I is an ideal in R. The theorem says that I is prime if and only if R mod I is an integral domain. So this is saying that I is a prime ideal is equivalent to R mod I being an integral domain. Okay, so let's prove this theorem. So we'll start with the forward direction. So I'll suppose that I is a prime ideal and a plus I and b plus I are elements of R mod I. What do I want to show? I want to show that R mod I is an integral domain, so I want to show that R mod I has no zero divisors. Right? We know that if R is a commutative ring with identity, then R mod I is already a commutative ring with identity, so our goal is just to show that R mod I has no zero divisors. Okay, so let's kind of write that down. I'll write it in orange. I'll say we wish to show that if a plus I times b plus I is equal to 0 plus I, then either a plus I is equal to 0 plus I or b plus I is equal to 0 plus I, right? Remember, zero divisors are elements that are non-zero and multiply to 0, and we want to show that those don't exist. So we want to show if that two things multiply to 0, then one of them is 0. Okay, so let's start this proof. Okay, so if a plus I times b plus I is equal to 0 plus I, then what do I know? I know that ab plus I is equal to 0 plus I. Well, then what does that mean? Well, if we remember our definition of equivalence, right? So these are two equivalence classes and we're saying that they're the same. This is the same as saying AB is congruent to 0 mod I. And so we know that AB minus 0 is an I. In other words, AB is an element of I. Okay, so we've unraveled this so far, and now we could say, okay, well, I is a prime ideal. So if AB is an element of I, we can say, okay, since I is prime, that must mean that A is an element of I or B is an element of I, right? In other words, that A minus 0 is an I or B minus 0 is an I, and so A is congruent to 0 mod I or B is congruent to 0 mod I. Thus, we have that A plus I is equal to 0 plus I, or B plus I is equal to 0 plus I. Right? So we can say, hence, R mod I is an integral domain. And that finishes the forward direction, an integral domain. Okay, so that completes the forward direction. Now let's clean up and do the backwards direction. So the backwards direction is going to be quite similar in flavor. So I'll suppose that R mod I is an integral domain, and I'll suppose also that A times B is an element of I for some A and B in R. Okay, well, what does that tell me? Then, using similar reasoning to before, I have that AB plus I is equal to 0 plus I. In other words, that A plus I times B plus I is equal to 0 plus I. Well, since R mod I is an integral domain, so since this guy is an integral domain, I know that A plus I is equal to 0 plus I, or B plus I is equal to 0 plus I. In other words, that A is an element of I, or B is an element of I. All right, A plus I equal to 0 plus I, we can go through the same reasoning. A is congruent to 0 mod I, so A minus 0 is an I, so A is an I, or similarly, B is an I. So I could say, hence, I is a prime ideal. And that finishes my proof. Okay, so we've answered the question of what kinds of ideals turn R mod I into an integral domain, but we haven't yet answered the question of what kinds of ideals turn R mod I into a field. So let's think about this a little bit more deeply. So I'll start with a commutative ring with identity, and there are two facts that I'll recall, and these are facts that I usually give as homework exercises. They're good problems to work on to kind of like test your knowledge with this. The first fact is that R is a field if and only if the only two ideals of R are the zero ideal and R itself, right? So this is equivalent to being a field. Fields only have two ideals, and any commutative rings with identity that have exactly two ideals are fields. And the key to this, if you want to try this as an exercise, is to use the fact that if one is in your ideal, then your ideal becomes the whole ring. Okay, so that's the hint that I'll give there. Another exercise that I like to give that's good practice is if I have two ideals I and J in R, and I know that I is a subset of J, then it turns out that J mod I is an ideal of R mod I. Okay, so when I form this ring R mod I, and I is in some sense too small, J mod I is going to be an ideal of R mod I. So I'm going to have ideals that may not be R mod I or the zero ideal. Okay, so what do I want to do? I want to choose an ideal. If I want to construct a field, I want to choose an ideal I so large that J cannot be between I and R, right? I want to choose an ideal so large that there can be no ideals between I and R, but I also don't want I to be all of R, right? I don't want because R mod R is isomorphic to the zero ring, and we know that the zero ring is not a field. Okay, so an ideal M subset of R is called maximal, and notice this notation. This is saying that M is a subset of R, but not equal to R, so it's a proper subset of R. I will call M maximal if for any other ideal J that is between M and R, we have that either J is equal to M or J is equal to R. So this is really capturing the fact that I can't squeeze any ideals between M and R. Okay, so the first type of maximal ideal is going to be the ideal PZ, where P is a prime. So let's show that this is maximal. Because we know that Z mod PZ is a field. It's not just an integral domain. So let's show that this is a maximal ideal. So I'll suppose that I have some sort of ideal I that lives between PZ and Z, right? And I'll assume that PZ is not equal to I. So now my goal is to show that I has to equal Z. Okay, so what does that tell me? Well, then I know that there exists some element A in I such that A is not an element of PZ, right? I have that I is strictly larger than PZ. So PZ is a proper subset of I. So that means there's something in I that's not in PZ. Well, I can say since A is not in PZ, I know that A is not a multiple of P. We have that the GCD of A and P is equal to 1. Okay, so the GCD, the only possible values for the GCD of A and a prime are either 1 or P, because the only divisors of P are 1 and P. Well, I know that P doesn't work because P doesn't divide A. So the only choice we have is 1. Okay, so then there exists integers u and v such that AU plus PV is equal to 1. But let's think about this for a second. If I have this element 1, this is equal to AU plus PV. Well, I know that A is in my ideal, so A times U is in my ideal. I know that P is in my ideal, so P times V is in my ideal. So 1 is an element of I. Okay, so what does that get me? Well, if 1 is an element of I, and let's say I take any other integer, then I know that n, which is equal to n times 1, is going to be an element of I. So hence, I have that z is a subset of I. Well, what does that lead me to? Well, we know that I is a subset of z. We've just shown that if 1 is in my ideal, then z is a subset of I. So I could then say, hence, I is equal to z, and so PZ is maximal. Okay, so we've shown that this is a maximal ideal. Okay, so here's another quick example of a maximal ideal. I'll suppose f is a field, and I'll take p of x to be a polynomial with coefficients in f, and p of x is irreducible. Well, it turns out that the ideal that p of x generates is maximal. And then what's the proof of this? The proof is actually identical to the proof that we just did for pz. Kind of just put an of x next to every symbol and replace all your z's with f bracket x, and the same proof holds. So the ideal generated by an irreducible polynomial is always a maximal ideal. Okay, and before we prove our next theorem, we actually need to prove a quick lemma. So lemma, think of it as like a stepping stone to a theorem. This is something we'll need to use in our next theorem. So the lemma says the following. The lemma says if I and j are ideals of a ring R, then I plus j, which is defined to be little I plus little j, where little I is in I and little j is in j, is also an ideal of R. Okay, so let's prove this fact. So the first thing I might notice is that I plus j is not empty, since I know that 0 is in I, 0 is in j, so 0, which can be written as 0 plus 0, is an element of I plus j. Okay, so I know that this is not empty because it contains 0. So now I just need to show that I plus j is closed under subtraction and that it absorbs elements of R under multiplication. So I'll say let I1 plus j1 and I2 plus j2 be elements of I plus j for some I1 and I2 in I, and j1 and j2 in j. Okay, so let's subtract these two elements. So I could say then I1 plus j1 minus I2 plus j2. This is going to equal I1 minus I2 plus j1 minus j2, and this is an element of I plus j since, well, I1 minus I2 is an element of I, and j1 minus j2 is an element of j, right? Ideals are closed under subtraction, so we know that if I subtract two elements of I get an element of I, and if I subtract two elements of j, I get an element of j. Okay, great. So we've shown that it's closed under subtraction. It remains to show that I plus j absorbs elements of R under multiplication. So I'll say let R be an element of R, and I plus j be an element of the ideal I plus the ideal j. Okay, so what does that tell me? Well, then R times I plus j, this is equal to Ri plus Rj. And then I notice that, well, I is an ideal, so Ri is an element of I, and capital J is an ideal, so Rj is an element of capital J. So this guy is an element of I plus j. And I plus j times R, this is IR plus JR. I notice that since I is an element of the ideal I know IR is an element of the ideal I, and since J is an element of the ideal J, then JR is an element of the ideal J. So we get that these guys are in here, right? And maybe we could write this over here, since RI and IR are elements of I, and RJ and JR are elements of J because they're ideals. Okay, so we've proved this lemma, and now let's use this in our main theorem. Okay, so now we're finally ready to prove our big theorem. So I'll let R be a commutative ring with identity and M be an ideal of R. The big theorem says that M is maximal if and only if R mod M is a field. So it turns out that maximal ideals are the things that give fields. Okay, so let's prove this theorem. So we'll first establish some basic facts. One thing that we'll be using quite often is something we used when we talked about prime ideals, but I'll be a little bit quicker about it this time, is that A plus M is equal to B plus M if and only if A minus B is an element of M. So we'll be using this fact quite a bit. So let's go in the forward direction. I'll suppose that M is maximal, and let's establish a few things. Well, the first thing we know is that R mod M is a commutative ring with identity 1 plus M. The next thing we know is that M is maximal, so M is not equal to all of R. So maximal ideals are ideals that are as large as possible without being all of R themselves. So what do we know? We know that 1 is not an element of M, and that gives us that 1 plus M is not equal to 0 plus M, using this fact in orange above. And now why do I care about 1 not being an M? Well, remember, 1 is an M implies that M is equal to your whole ring, right? If 1 gets inside your ideal ends up being your whole ring, right? So the point is 1 is not an element of M because I know that M is not equal to R. So 1 plus M is not the same as 0 plus M. Okay, so those are some basic facts. It remains to show that every element of R mod M is a unit. So let's clean this up and do that. Okay, so let's continue with the forward direction of our proof. We need to show that if I take a non-zero element of R mod M, then that element ends up being a unit. So I'll suppose that A plus M is an element of R mod M, and I'll suppose that A plus M is not equal to 0 plus M. And what this means, using this fact in orange, this is just saying that A is not an element of M. Okay, so now I need to use the fact that M is maximal. So I'm going to use the lemma, and I'm going to say consider the ideal generated by A plus M, right? And the thing to note about this ideal is that M is a proper subset of the ideal generated by A plus M, which is a subset of R, right? The thing to notice is that A is an element of this new ideal we've just created, but A is not an element of M itself, right? We're starting with the fact that A is not an element of M itself. Okay, so we have that this is a proper ideal, and well, we have that M is a proper ideal of the ideal generated by A plus M, but I know that M is maximal. So I could say, since M is maximal, I'm forced to conclude we have that this new ideal, A plus M, is equal to all of R, right? There can't be any ideals between M and R unless that ideal is equal to M or it's equal to R. We've already established that this new ideal is not equal to M, so this new ideal has to equal R. Okay, why is that useful? Well, we know that 1 is an R, so we know that 1 is an element of the ideal generated by A plus M. Well, what does that tell me? It tells me that then 1 can be written as AR plus little m for some little r in R and little m in M, right? So this portion is coming from the ideal generated by A. This portion is coming from here. Okay, but then I have that AR minus 1 is equal to negative m is an element of M. So using the fact in orange, we get that AR is equivalent to 1 mod M. In other words, AR plus M is equal to 1 plus M. But what does that tell me? So I can say then A plus M times R plus M is equal to 1 plus M. Hence, we've shown that A plus M is a unit. Okay, and so R mod M is a field. Right, we found a multiplicative inverse for A plus M. Okay, so now we can do the backwards direction. Okay, so now we're ready to tackle the backwards direction. So I'll suppose that R mod M is a field, and my goal is now to show that M is a maximal ideal. Okay, so first thing, let's establish that M is actually not equal to R. Well, one thing we know is that in any field, the multiplicative identity is distinct from the additive identity. So we have 1 plus M is not equal to 0 plus M, which means that 1 is not an element of M, and so M is not equal to R, right? 1 is an element of R, but it's not inside of M, so M and R are two different sets. Okay, so now let's consider an ideal. Let J be an ideal satisfying M is a proper subset of J, which is a subset of R, right? My goal is to show that J is equal to R. I want to show that M is maximal, so that if there's any ideal that lands between M and R, then it's either equal to M or it's equal to R. So I'm going to take an ideal where M is a proper subset of the ideal. I want to show that J is equal to R. Okay, well, let's think about this. If M is a proper subset of J, I could say then there exists a J in J such that J is not an element of M, right? In other words, using the fact in orange, we have that J plus M is not equal to 0 plus M. Well, what does that tell me? Since R mod M is a field, so I could say since R mod M is a field, well, J plus M must be a unit. So I can say there exists a K in R such that J plus M times K plus M is equal to 1 plus M. So let's rewrite this. If I rewrite this, this is going to tell me that JK plus M is equal to 1 plus M. Right, so I'm just using my definition of multiplication and R mod M here. Well, what does that tell me? It says then, using my fact in orange, I know that JK minus 1 is an element of M. In other words, that JK minus 1 is equal to little m for some little m in my ideal M. Okay, so where does this lead me? Then I know that 1 can be rewritten as JK minus M. And the thing to notice here is that this guy, well, I know that J is an element of J, so JK is an element of J, so this guy is an element of J. And this guy right here is an element of M, but that's a subset of J. So what do I get? I get that 1 is an element of J, and so J is equal to R. Hence, I know that M is maximal. Okay, and this completes my proof. Okay, so now we're ready to explore some corollaries of this theorem. So the first corollary is rather easy, based on what we showed before. We know that if P of X is an element of F bracket X, then the ideal it generates is maximal. So we get right away that F bracket X mod the ideal generated by P of X is a field. Now, why is this interesting? Well, this is interesting because we can use this corollary to construct finite fields that don't have a prime number of elements. So up until this point, we've seen infinite fields like R and Q and C. We've seen fields with a prime number of elements like Z mod P, and we saw one example of a field with 4 elements. So now it turns out this theorem allows us to construct fields with P to the n elements. So how do we do that? So I'll say let P and Z be a prime, and I'll take Q of X in ZP bracket X to be irreducible, and I'll take the degree of Q of X to be n. Then if I consider ZP bracket X mod the ideal generated by Q of X, let's think about what this looks like. The thing to remember is that any polynomial in ZP bracket X is going to be equivalent to its remainder mod Q of X. So if the degree of Q of X is n, the remainders all have degree n minus 1 and lower. So the elements of ZP bracket X mod the ideal generated by Q of X are all polynomials of degree less than or equal to n minus 1 plus our ideal. This is what the cosets look like. And of course, the coefficients come from Z mod P. And we have that this is a field with P to the n elements. Why does it have P to the n elements? Well, if you look at what the cosets here look like, what the elements of this ring here look like, I have p choices for a0, right? I can choose a0 to be 0, 1, 2, all the way up to p minus 1, because I'm working in z mod p. I have p choices for a1, I have p choices for a2, so on and so forth, and I have p choices for an minus 1. So I have n spots to fill, and I have p choices for each slot, so that gives me p to the n elements. So this is kind of neat, because now I can construct a field with p to the n elements if I can find an irreducible polynomial in zp bracket x. Okay, and finally we have one more interesting corollary that's going to use both of our theorems. So again, we're in the setting that R is a commutative ring with identity, and the theorem says that if M is maximal, then M is prime. So how can I show this? Well, let's try this. So I'll say M is maximal. Well, this implies that R mod M is a field. Well, we know that every field is an integral domain. So this implies that R mod M is an integral domain. And then finally, I know that if R mod M is an integral domain, I know that that means that M is prime. So M is a prime ideal. And that's it. It's my corollary. So every maximal ideal is prime. One thing I will point out is that not every prime ideal is maximal. So for example, if I look at z bracket x mod the ideal generated by x, this is going to be isomorphic to z. So what do I get? I don't get a field. I get that x is prime, but not maximal. Right? Why is it not maximal? Well, it's since z is not a field. And we could actually find an ideal. I can take x. This is properly contained in the ideal generated by 2nx, which is properly contained inside of z bracket x. So we can actually find an ideal in between those. But the kind of reason here is that the ring that I'm getting is not isomorphic to a field, it's isomorphic to an integral domain. So since z is not a field, I know that this ideal is not a maximal ideal. Okay, and finally, I'd like to go back to one more example from the quotient ring and first isomorphism videos. So I'll consider R to again be the set of functions from the reals to the reals. And remember, this is a ring under pointwise addition and pointwise multiplication. And I'll let I be all the g in R such that g of pi is equal to 0. So these are all the functions from R to R where g of pi is equal to 0. In our first isomorphism video, we showed that R mod I is isomorphic to the real numbers. Well, what are the real numbers? The real numbers are a field, right? So we have that R mod I is going to be a field, and this shows me that I is a maximal ideal. All right, so this is kind of a nice application of the theorem. I'm able to show that I is maximal just by showing that R mod I is a field.